In this video, we'll be looking at PID control, which is a way of making movements more reliable and accurate in robotics. For example, if you have a differential drive robot like this one that you want to drive in a straight line, but one of the motors is more powerful than the other one, it will start to veer off course, and you need to measure how fast the robot is moving and correct for that. This is also what helps robot arms to have more smooth movements, and hence do their tasks more accurately and reliably. We're going to dig into what each of the P, I, and D components do in a PID controller using an interactive component that I built specifically for this purpose. But first, let's try and define some control theory terms so that we have a good language for the rest of the video. Here we are in a smart whiteboarding app so that I can do some interactive illustrations for what these control theory terms mean. So we have these terms on the left, starting with PID control that we've already talked about, and we know that it is a form of control. So let's talk about control. First thing to define is a set point. So a set point is essentially the output that we are asking of the system. So let's say that we have a tank of water that we're trying to keep hot at the same temperature. This is what the set point would look like, where on the vertical axis you're looking at temperature and the horizontal axis is time. You might also have, after a period of the water being hot, you might decide you don't need the water to be as hot because people have stopped showering or running hot water. And at that point, your set point might drop down low again. So this is the set point in a control system. A controller is the process that keeps the output at the right level. So if we're trying to keep water hot and it slowly cools off over time because it's in a tank or people are using bits of it, maybe the water temperature would slowly drop and something needs to tell it to warm up again. And that something is the controller. So the controller might say, oh, the water has gone too low. We need to heat up. So it heats up very quickly and then stops heating again so that it will again tail off back to the right level. So that would be a controller that does that. For a tank of water, it would be a central heating system. If you're driving a car and keeping it at the right speed, then that would be the driver of the car, for example. So that's essentially what a control system does, what it's responsible for. It says, I'm meant to be here. What do I do to make sure that the output is at the right level, at that set point? So this diagram here shows how all the components of a control system fit together. First, our set point we've already mentioned. So that's the input to the system. Please keep it at this level or change to this level. It's the expected output of the system. Then our controller is here, so our process for setting the output of the system. And the controller produces a system input. So a system input here, which we haven't defined yet. So when the water drops too low and the controller says to increase the temperature of the water, it's essentially saying from no heating at all, start heating, and when the water's hot again, stop heating. So this would be the system input. It's what the controller produces to actually make something happen. Then in this case, the system is receiving this signal. If the signal is 0, it knows not to heat the water. If the signal is 1, it knows to heat the water. So that's what the system does. And the system response is this blue line. It's the actual temperature of the water. Now, what we also have is the system response, the temperature of the water, can be measured by some sensor. So we assume that the sensor is perfectly measuring the actual system response. Maybe our sensor is slightly off and the actual temperature of the water is slightly lower if it's miscalibrated or something. But for the most part, we don't tend to worry about that. We tend to just assume that the measured output is accurate. It's the same as the system response. So the sensor produces the measured output, which would be this blue line, that the controller can then use to decide whether to turn the hot water on or not. So it would measure the difference here, and that difference is small, so it doesn't do anything. And it would measure the difference here, and that difference is large, so it decides to do something. So that's a simple control system. So let's check that we understand all these terms. We know what a system input is. It is this red line. We know what the system response is. It's the blue line. And the system output just means the same thing. Different people call it either a system response or a system output. We've also got our measured output, which is what the sensor is producing. And as we said, we assume that's the same as the system output. And then we have these two terms, open loop and closed loop. These are two different types of controller, and they're determined by whether there is a feedback mechanism or not. So if we take our tank example and we remove the line where the feedback is fed back into the controller, this is now an open loop system. It means there's no actual loop here. It's just the controller is predicting what the tank should do. So it might say, I need to heat the water at a particular time. I'm going to assume the water is this temperature, so it needs to be heated up by this much. Now you can imagine that that works a lot of the time, but over time it can go out of sync. The water temperature doesn't quite track where it thought it was going to be. So over a long period of time, the water will stop being the temperature it needs to be, and the open loop controller doesn't control it effectively. For some applications, that's fine. For a water tank, you want a closed loop system. You want to have some kind of feedback. So that's the other form, the closed loop. If we remove this box again, the loop being closed starts at the controller, goes through the system, through the sensor, and back to the controller. So you see that this data is going around in a loop, and that's where the closed loop name comes from. So by providing some kind of feedback into the controller, we're closing the loop on our control system, which allows it to behave more accurately. Let's take another example, which is driving a car. So this is all available on my blog, which is linked in the description, which is very similar to what the video will have, but it gives you some of the images and you can take a look. And it's where the visualization tool is as well that I'll introduce shortly. But from here, imagine that we are trying to drive a car. We're driving a car from a village out onto a main road, which means we need to speed up. So if we're traveling at 50 kilometers per hour and then we want to travel at 90 instead to join the main road, that is our set point change. And you can imagine that ideally we want to accelerate immediately to 90 kilometers per hour. That's not how a real system behaves. We can't immediately follow the line. Instead, what normally happens is you can accelerate. So once we reach the set point, you can start to accelerate until you meet the line. Or if you know you're about to speed up, you can start to accelerate beforehand. So this is how a human might behave. But let's assume that instead of a human, we've got some kind of computer running it that we're programming. What algorithm do we tell the computer to use to speed up correctly? One example is that we might tell the computer once it receives its set point change, it should accelerate until it's the right speed, and then it should stop accelerating. So that's quite simple. But what happens is that when it reaches the top, it will overshoot because the car is still accelerating. So it needs to slow back down again to the target speed. So what happens is we slow back down and reach the speed, and we've broken the law by going too fast. So in this case, we can't just use the simple version of the algorithm. We need to do something a little bit more intelligent. And you can see here that I've got the graph describing the same thing. One option that we have for changing our system, instead of accelerating until we're at the correct speed, we'll measure the difference between our current speed and the speed that we want to be at. This is called the error. And we can do some kind of multiplication. So let's say that we're going to accelerate by half of the error. So if we do that, it will keep accelerating up until it reaches near the top, at which point it should smoothly join the line. Because we aren't accelerating at our full acceleration near the limit, we're slowing down. That means that we can more smoothly join the line. So this is one example of a P controller. And you can imagine that if we multiply by 0.5 and get this line, then multiplying by 0.75 would give us a steeper line, but with a similar behavior. This is the start of our PID controller. So let's talk about more of the components of the PID controller. So here is a diagram of what the PID controller is doing. And what this is, it's the controller box expanded out. So all of this fits in this box. And you can see here that there's a set point, which is here, and it's producing the system input, which is here. So our first step is to figure out the error, which we've already defined. but if we had a graph and it showed our set point was here and our actual value is here, then the error is the distance between it. So by subtracting one from the other, we actually get the error value. How far off from the system output are we? And if this system goes over, then our error becomes negative. So now we can finally define the three key terms of the PID controller. It's P for proportional, I for integral, and D for derivative. So what happens is the proportional term is a straight multiplication of the error. So the error goes in, is multiplied by a value, and that's the P term. So if our error is here, we multiply it by Kp, and that's the P term. Very simple, and the simplest version of what we've got. So in the driving the car example, when we multiplied the error by 0.5, that was a P controller producing a P term with a Kp of 0.5. Kp 0.5. But we can get more complicated than this. We can get the integral value. We can get the integral value, which adds up the area over time. So if you imagine that over time, we have this error value and we keep track of it, we keep track of the running total, then what we're doing is tracking the area between the curve and the set point. This is what allows us to correct for steady state errors. For example, if we have a system output that is just above, but not quite at the set point, then this error will get larger and larger over time to the point where the controller has to correct for it. We'll see this more in the visualization. The value that we're adding up over time is then multiplied by a parameter, ki, to produce the I term of the controller. So what this means is we take our error, we multiply it by kp to get the p term, we add it up over time and multiply that by ki to get the I term, and then our final term is the derivative term. The last term is the derivative, which is essentially how much the error has changed since the last time it was checked. So if we have two large errors, the difference between here and here is very small, so the derivative is very small. However, when there's a curve, the change between here and here is relatively large, so our D term becomes bigger. So whatever the derivative is of the error, then we multiply it by kd to get the D term. So overall, we take our error, we multiply it by kp for the p term, we add it up over time and multiply by ki for the I term, and we take the change from the previous time step and multiply it by kd for the D term. And by doing that, we can get an initial system input from the P term, which is quite close, an additional I term, which helps correct for steady state errors, and a D term, which stops us from correcting too much. And this provides what we call damping. It means the controller doesn't respond too fast to a change. And we'll see where this is useful with the visualization tool. So let's take a look at the visualization tool. This is the visualization tool. So I've built this tool to help give an intuitive understanding of how the P, I, and D terms work in a PID controller. And what we have here is a system, which is a robot arm joint moving a heavy payload. So if we add a P term in, what happens is it tries to move the arm up, but because the heavy payload drags it, it tries to move it back down again, and then it keeps doing that over and over, so the system oscillates over time. And you'll see this a lot in control systems where when you put too large of a P term on, it overshoots. Just as with our car driving example, if you accelerate too fast, you can overshoot the line. The same is true of a lot of control systems. If you increase kp too much, then it will overshoot the line and oscillate around it. Thankfully, this is where we can add the second of our terms. Now, I'd recommend just going with derivative term because adding integral makes the graph go crazy. We can add a derivative term in, and even something very small, what we're doing is damping the oscillation. So by increasing this term even just a little bit, it's starting to make our line a lot flatter. And if we increase that even more, we can make the line go up and then smoothly come to a flat line. And this is great. This is getting much closer to what we want. And you can see that by introducing more of KD, we're damping it more and more. So if we increase this too much, we're slowing down the response of the system. So we want to keep this so it's just giving us a good response, maybe here or one step on. so it's smoothly coming to a flat line. So if we move this time slider along, we can see a few things happening on the graph. First, it prints out the errors that it is currently receiving. The error here is 0.5 because the line has flattened at 0.5 and the set point is at 1, so the error is the difference. We can also see the derivative value is 0, which is shown by this purple line. So when we have a big increase in error, you can see the purple line is sloped up quite large and the line is longer. And if we move it along to the flat portion, the derivative is now 0. And the last term that we haven't looked at yet for the visualization tool is the integral gain Ki. So what we're showing here is by shading the graph, the integral is increasing over time. And as we keep going on, the integral goes up and up and up. And that's because we have a steady state error. Even though we've got a P term and a D term, we're not actually reaching the set point that we're meant to get to. So what we can do to fix that is to increase the integral gain. And you can see by putting it up a small amount, the line is starting to reach towards the set point. And if we go further, we start to reach it. So here, this is a reasonable system response, but it's pretty slow. So now what we can do is start to tune it. We can start to play with the parameters to get this line as close to the set point as possible. So let's decrease derivative, increase proportional, increase integral. There we go. So we have a line that is better. It's still not quite where we want it to be, but it's still matching the set point pretty well after 4 units, whatever those units are on this graph. So what we can see here is that different PID parameters, Kp, Ki, and Kd, need to be tuned for different systems. In this system, these values give a good response. They give a response that is fairly close to the set point. We can't get a pure vertical because it's modeling a system that can't accelerate infinitely fast. So it has to curve up and meet the set point as we want it. Now that we've got the parameters tuned fairly well, we can start to see what effect each of them has on the output of the system without the oscillation that was going on before. So first, with our proportional gain, we can see that reducing it will reduce the system response, so it takes longer to get to the set point. And if we turn it up a lot, the line becomes much larger. And that's because it's got a very fast response, a very high proportional gain. Let's set that back to about there. If we put our integral gain too low, we have steady state errors. And if we put it up too high, we start to see that same oscillation that we're trying to correct for in the first place. It is overshooting, exactly the same as having too large a proportional gain. So you can set that back down again. And our derivative gain, if we increase it, we are damping it more. We're making the system response slower. So this line takes longer to reach the set point. And it also affects the others so that they overshoot. And if we lower it down, it has less of a damping effect on the graph itself, and it means the system response can be faster. So some amount is good, but too much makes the system response slow and unreliable. So as you can imagine from this, different parameters are needed for different systems, and this is a process known as tuning the controller. For each system, we need to figure out the right values of Kp, Ki, and Kd to get a good response from our system. A word of warning is that this is very hard to tune if you're not using the real robot, because there's so many different things that you don't account for when you build a model for it. What you're trying to do is compensate for the real system and the real things that happen that you haven't built into your model. So if you're tuning a PID controller for a real robot, do it on the real robot. It'll give you a much better response if you do. Also, there's an issue with derivative gain, which is that because it acts on the error between 2 subsequent points, if you have a lot of noise in your sensor, so it jumps up or down sharply when the real value doesn't account for that, it's just the sensor being noisy, that can give you a much bigger response than you expect, meaning the controller doesn't behave very well. So try and keep derivative gains small because it makes the system more sensitive to noise. And that's our 3 parameters, P, I, and D, which brings us onto the 4th optional parameter, the feed-forward gain. And we get this from the ROS2 control implementation of the PID controller. So I've talked quite a bit about ROS2 control on the channel using videos and blog posts. ROS2 Control provides pre-built components to control your robots moving around. One of the controllers it provides is the PID controller. Exactly as we've been talking about, it can help you to define a controller to control your robot where you set the values for P, I, and D. You can write your ROS2 control system as normal, and then use a PID controller to control your system. And then all you need to do is set configuration to use the PID controller and set its parameters. So you can see an example of this at the bottom with its example parameter file. You can see that for a particular joint, it's setting a value for P, a value for I, and a value for D. And that's KP, KI, and KD respectively. And here's an example of the last parameter, the feed-forward gain. And that gives the controller a base to work on that makes it easier for the other components to do their work. So to understand this more, let's take a look at the whiteboard again. So here is our PID controller with the 3 terms, but we're going to add a 4th term, and instead of taking it from the error, we're taking it from the measured output. So that's how this term is different. It's essentially trying to correct for a difference in the measured output before it ever reaches the controller. It's providing a base for the controller to act on top of. So the measured output is taken and multiplied by another constant, KFF, and then that is also summed into the box with the rest of the terms. So instead of acting on the error, it acts on the measured output. So let's see the visualization tool to understand how it helps. Here we are, we've reset all the parameters, which you can do by clicking Reset PID. And we're going to increase feed forward to understand what it does to the system. So if we increase it to about 0.5, we can see that the oscillation is almost exactly around this line, but it also goes down really far. So now if we put our parameters back on, there's our derivative term and a little bit of proportional. And you can see that from here, our KP and KD are much lower. Our integral is 0, and our response is as good or better than it was before. So for this particular system, feed forward has really helped. And this is an optional term, but depending on the system you're controlling, it can come in very useful. So now we've seen the P, I, and D terms and the feed forward term for use in the parameter file for ROS2 control. We could take this and plug it into a real robot, assuming the system is already built to control the robot, and then start tuning the parameters to get a good, reliable, stable response from our robot. In this video, we saw how PID controllers can make our robots more stable, accurate, and reliable, which is why they're so widely used in robotics. It's a form of closed-loop control, which means it takes the measured output from the sensors and subtracts it from the set point, which is where it ought to be, in order to determine how to compensate for the difference. It has the proportional term, which is a straight multiplication of the error, the integral term, which adds up the error over time to get rid of steady-state errors, and the differential term, which measures the change in error and reacts accordingly. By tuning these 3 parameters to be stronger or weaker, we can tune our PID controller to whatever system we need, and it can be used to compensate for almost any system, which is why it's so popular and widely used. We also have a 4th optional term, the feed-forward term, introduced by the ROS2 control implementation of a PID controller. And instead of acting on the error between the measured output and the set point, it acts purely on the set point, giving a base for the PID controller to act on top of, which means that the other components don't need to work quite as hard in order to compensate. In our example with the interactive component, we saw a robot arm joint being modeled, and we saw that by adding a feed-forward term, we didn't need any integral term whatsoever to get a good response. If you've managed to develop an intuitive understanding of how PID controllers work, it's time to use it for real on a real robot. See if you can get a real robot and tune it to be more accurate using a PID controller. This is exactly what I'll be doing in a future video using the ROS2 control implementation of a PID controller.